Thank you very much, Sakia. Let me begin by thanking the organizers for organizing this really interesting symposium. I want to sort of build on what we've heard already in this morning, starting with the panel discussion and this whole challenge of being able to print electronics on flexible substrates. And we've all heard of all the advantages, but just to remind people from a fundamental materials perspective, we're going to need some unconventional kinds of materials, N-type organic conductors for organic CMOS. We're going to need better gate dielectrics. We're going to need a better understanding of charge transport, fundamental understanding from single crystals to films to printed whatever. And the basic building block, of course, is going to be the field effect transistor. So what I want to talk about this morning is sort of give you a brief update on three overlapping areas in our group. And let's see, I should really use the remote. So first I want to talk about some new developments briefly in organic semiconductors, in particular the challenge of making N-type materials. And you'll see how this fits in with some of the earlier talks we've had. And then I want to talk about gate dielectrics. You might first think, what could be more boring than something that doesn't do anything, right? It just provides resistance. But in fact, if you look at the developments, say, of hafnium dioxide gate dielectrics and how that's revolutionized silicon technology, you begin to think of how important it is. And then the last, I want to switch back to semiconductors, but I don't want to talk about organics. I want to talk about amorphous oxides and show you some new results there that I think are really thought-provoking. The main focus will be transistors, but I'll show you how this fits in with photovoltaics as well. So the basic design principle for making organic N-type conductors, and we want those which are processable, printable, air stable, environmentally stable, moisture stable, is to design building blocks where we drop the energies of the LUMOs so that the electrons which are going to be transported are now low enough in energy they don't react with oxygen. We want solubilizing groups to drop the energies of the LUMOs. You can see on the diagram we want electron withdrawing substituents which drop the energies of the HOMOs and LUMOs. As we get better and better at making the building blocks, which you'll see in themselves are interesting molecules, we're then going to connect them and make polymers for processability. So I'll just give you a brief overview of some of the latest results. One of the things we've learned as we've explored the synthetic chemistry here, and I really want to impress on you how important it is to do the right synthesis, but to have it coupled with measurements in theory, chemists, physicists, material scientists, is that we've learned how to tune the LUMO levels. And as you can see here, I really hate to do this because there are two screens, but you can see here we drop the energy of the LUMOs, we reach a point where air stability sets in. And so below this point here, all of these materials are air stable. And I think it really resonates with some of the talks we've heard already. This is a non-trivial problem if you're going to manufacture whether or not something is air stable. So this is one thing we've done. Another thing in that regard has to do with how do you design building blocks for air stability. And what I'm showing you here, and please just focus on the inset here, is going from a dithiaphene to a dithiaphene. We want to maintain coplanarity of the heterocyclic rings for maximum charge transport. As I begin to put groups on them, you can see we bend it out of coplanarity. And so you say, well, one way to force it to coplanarity are these weak secondary interactions here. And this is donation from an oxygen lone pair into an empty sulfur orbital. And this will lock them into a coplanar orientation. But when I add these methoxy groups, look how the HOMO goes right back up in energy. And you can't live with that because it's too electron donating. So we add nitrogens in the ring. And nitrogen has the effect, you can see, compare these numbers to those, to those, to those, of dropping the energies of the HOMOs and LUMOs. And the effect they have on these transistors is very easy to see here. So what I'm showing you is transfer plots. This is just the cyclic voltammetry showing we can shift with the nitrogen substituents, the onset of the oxidation. But a better way to see it is to look at these thin film transistors. Maybe I should point over here also. And you can see as we add nitrogen here, we greatly increase the on-off current And this is lifetime data, and I'm showing you 6 weeks, but I could show you a year, and dramatic enhancements in the stability of the devices by introducing nitrogen atoms in the heterocycle. Finally, we've learned enough about tuning these materials that with this copolymer, so copolymer meaning there's a thiophene, there's this linking group, and then there's this very electron-rich group. These are p-type. We can modify this structure, this intermediate structure, in another way and make it n-type. And you might say, well, so you made some n-type and some p-type. So what's the purpose of that? We know from the mobilities of organic semiconductors that we're going to need CMOS. We're going to need complementary circuits with N and P-type transistors to get maximum performance. That's a given. So this is just showing now we've made a complementary inverters. We've made lots of other devices. Polycrystalline, which is our spin-off company, has made structures now with 1 million transistors. And this one happens to be by inkjetting. And you can see quite reasonable performance, completely air stable, all processing under air. So if you're really good at getting the mobilities out of these polymers, tuning the band gap, you can do this. And this is the final polymer slide I want to show. So this is a polymer with donors and acceptors in the main chain. And as I said, you can use this to tune the work function and the mobility. But you can also use it to shrink the band gap. And we can put them then, this is an inverted solar cell. So it's got zinc oxide and molybdenum oxide as the PIN layers, if you like, the interfacial layers. This just shows you an electron micrograph. So this is our first generation polymers, and reasonable mobility, reasonable power conversion efficiency, reasonable everything. But the latest generation, when we tweaked these, and that just came out in Nature Photonics, fill factors of 80%. 80% has never been found that high in an organic photovoltaic. And it has a lot of interesting promise that if we can boost the power conversion efficiency, the band gap here is still fairly wide. The interplanar spacing between the chains is very, very small, that we can do a lot better than 8.7%. So there are implications in this semiconductor polymer design, not only for transistors, but also for photovoltaics. Let me go to the second topic now, and let's talk about the gate dielectrics. And if you think of what a gate dielectric does in a transistor, it's like a capacitor. So it stabilizes the carriers in the channel, and the source drain current will scale as the mobility of the material, not maybe the greatest for organics, the gate voltage, and the capacitance of the gate dielectric. So the capacitance, this is exactly what Intel came up against when they went from silicon to hafnium, why they went from silicon dioxide to hafnium dioxide. It scales as the K of the material, the dielectric constant, divided by the thickness. So for materials that we wanted to print and process at room temperature, we couldn't use hafnium dioxide. And I can tell you, even if you use ALD hafnium dioxide, it's not as good as the dielectrics I'm going to show you. So the materials in the right panel here are called SAND, self-assembled nanodielectric. And it's basically a modular layer-by-layer deposition of organosilane linked structures that have high Ks and are very, very thin, and that's very important. And so the thicknesses here are from X-ray reflectivity. Just to give you a sampling of what these can do, in our hands, almost any inorganic semiconductor we've used them with, we saw far better performance, whether it's carbon nanotubes or zinc oxide, indium oxide nanowires, gallium arsenide, oxide thin films. I'll show you some examples. The panel on the left is work with John Rogers using his silicon nanomembrane TFTs. What do you see? You see reduced hysteresis, the transfer plots, reduced operating voltages. They're very radiation hard, and this actually went up on the International Space Station. Here's our devices there. Testing for radiation hardness, they did very well. This is an monochrome OLED device we made with no silicon. So the driving electronics are zinc oxide nanowires and sand. So you might say, well, all right, so show me, what is this dielectric what'll it do for me? This is early work with John Rogers, and his group was making carbon nanotube transistors. They're using silicon dioxide as the gate dielectric, 100 nanometers. And look at this transfer plot here. It's ridiculous. This is hysteresis. It's due to trap charge between the semiconductor and the gate dielectric, and sand suppresses that wonderfully. So here is the same device with a sand gate dielectric instead. Look how the operating voltage is dropped, and there's negligible hysteresis. So you might say, yeah, but those are really not very good carbon nanotubes, and the sand you showed us, you have to process ideally under nitrogen. So now we have new generations of sands, and I'll tell you a little bit about them, that you can process under air, and they're multi-layer structures with zirconium or hafnium layers, and the same kind of pi organic sandwiched in between. The pi organic gives you the large K. The saturated organic parts, as I show you here, are the hafnium dioxide, gives you the insulating characteristics. And here are two variants of sand which are vapor deposited, one combined with ALD alumina. So you can either do hydrocarbon solvents with inert atmosphere, you can do ambient growth with alcohol, water solvents, or you can use solvent-free materials. Let me just show you a couple examples of, first of all, how we make these. So this is the zirconium sand, and it's basically a dipping process where we interleave zirconium oxide, a kind of sol gel material, with the organic pi system. And if you look in the right panel here, you can see it works. These work really well with pentacene transistors, with zinc tin oxide. The K here is about 11, very, very low leakage. This just shows you the capacitance as a function of frequency. And finally, in the upper right panel is the TEM, very, very regular structures. I'll show you some X-ray reflectivity in a minute that'll underscore that. So they're very nice materials, stable at 350 C under air. This is an example now. Let's come back to the carbon nanotube story. This is work with my colleague Mark Hirsum, and his group has perfected a way to get very, very pure carbon nanotubes, separate them from the metallic nanotubes. And so if you look, this is transconductance versus gate voltage. This is on silicon dioxide, so it's a transfer plot, really awful. This is the carbon nanotubes on one layer of the vapor-deposited sand. And if you compare the plot mobility versus on-off, most of the world is over here, and our best are over here. And just recently, we reported mobilities of about 150, very small subthreshold swings. You can make very, very good carbon nanotube transistors. The student wanted to try hafnium oxide sand. So and we thought, well, it's going to be like the zirconium. It's not quite. It turns out the surface chemistry of hafnium oxide is a little different. So it actually chemisorbs more of the organic part that gives you the K. And so now we're above 1 microfarad per centimeter squared in the capacitance. So that's very, very large. We're really excited about this, very robust materials. I don't want to go into it in great detail, but this is X-ray reflectivity, just to show you. So this is the reflectance, and now we've done the Fourier transform. There's the electron density, 4 layers, 1 layer. These are very, very regular structures. And this just shows you its X-ray fluorescence, that the hafnium oxide absorbs a little more of the organic than the zirconium does. So at this point, you might be thinking, well, isn't there some guidance in terms of how do you make one of these high K nanoscale dielectrics? And so this is work with Mark Ratner and a student, a very bright student named Henry Heitzer, developing basically a first principles method, starting with organic monolayers with different building blocks. So it's a plane wave DFT calculation to actually predict what the dielectric constant of organic layers like this will be. So this is just looking at layers of benzene, fluorobenzene, and chlorobenzene. And what is plotted here is actually the dielectric constant along the axis of the molecule. This is another study where he looks at, as we increase the density of molecules in the monolayer, how this scales with coverage. So we understand this very well. Now you might be saying, yeah, but connect it with reality. What does calculated versus experiment look like? So this is the computed capacitance for a benzene crystal, 2.39. This is what's in the literature, 2.34. And we have a number of other cases where we hit it within 5 or 10%. So we have the armamentarium now to really start predicting the properties of these dielectrics. Let me come to the last part of the talk. And I talked a little bit about printed electronics, but I want to focus a little more on transparent electronics. And that ties in with OLED technology very, very, very well. So imagine that you could have a decal on the windscreen of your car that had the GPS information, or for aeronautics, transparent laptops. Here's a Samsung transparent OLED. Don't guarantee all the customers can do that. This is now one of the interesting materials that is sort of coming on the scene is indium gallium zinc oxide, IGZO. And this is just from the Sharp website, so they've perfected this, but much better mobilities than amorphous silicon and optically transparent. So takes up much less real estate on the display. And this is just Sharp showing you, here's amorphous silicon, and here's IGZO, how you can miniaturize the pixel. So that's really exciting. But let's talk about oxide electronics. And this is something, I'm not just an organic chemist, I'm a materials chemist. We got very interested in. And the reason is, first of all, let's go back to ITO. Why is an inorganic oxide optically transparent? Well, the theory had been worked out by Goodenough and Freeman and Medvedeva and Zunger. But the valence band is largely p orbital, sorry. This is energy and density of states. So there are always these heavy post-transition ions. And the conduction band is S states. So that's kind of unusual. And as you go from indium oxide to indium tin oxide, the tin dopes the structure and puts in these electrons. And so if you want to make a TCO, like ITO, you want to dope it. We don't want to dope it because we want to make this for semiconductors. We can dope it for source and drain electrodes. So this is our first foray. This is an indium oxide transistor. It was grown by the indium oxide by ion-assisted deposition. If you look in this stack here, you see an ITO gate, a sand dielectric indium oxide grown at room temperature by ion-assisted deposition, and then doped indium oxide source and drain electrodes. So completely transparent. This is 70 transistors. The mobility here is very, very large, so it blows the organics away, 130 very small subthreshold swings. So at the time we were really excited about this. But I want to turn now, that was indium oxide, which was polycrystalline. I want to turn now to amorphous oxides. And everything we learned as undergraduates, right? If you want to have a high mobility, you want a nice crystalline ordered lattice. So what is this, these amorphous materials? And here, this is the XRD and the electron diffraction, completely amorphous. You can grow them at room temperature, and I'll show you lots of ways to grow them. High mobility, how can you get that? And I'll show you that in a minute. Low deposition and processing temperatures, very, very smooth surfaces. No grain boundaries, they're very flexible. I'll show you that. Optical transparency and tunable properties. Hosono was not the first person to discover these, but he was the first person to bring it to the attention of the world. And it goes back to the band structure picture I showed you, why you can have these kinds of mobilities. Here's amorphous silicon, covalent bonding, all sp3 bonding, all of these dangling bonds in the gap, so big differences in mobility between amorphous and crystalline. On the other hand, for the oxides, where the conduction band is S-based, very flexible isotropic orbitals, you can bend the bonds in lots of directions and still get very good mobility, along with things like mechanical flexibility. So let me tell you about some of these materials and what you can do with them. The first way we grew them was by pulse laser deposition. Not a manufacturing process, obviously, but just to illustrate what they can do. And this shows you our stack then. ITO is the gate dielectric, sand, And then this is amorphous zinc indium tin oxide. Why do we want to mix all of these ions together? If you want to frustrate the crystallization, you put in small ions, large ions, some ions which are known to frustrate crystallization. And so this is our amorphous semiconductor, and then we can modify the properties and make it conductive. So the mobility is 160 centimeters squared per volt second. On PET, rather than glass, the mobility is about 110. Minimum hysteresis, nice optical transparency. So that's good, but you might say, wait a minute. You started off, you were telling us you were going to print things, and you're using pulse laser deposition. So let's go one step further. The traditional problem with sol gel techniques, which you might think is the way you want to deposit a solution film, is you have to process them at very high temperatures to densify the lattice. You have to put the thing in an oven. And if you're on a plastic substrate, that's going to be bad news. And so we hit upon a technique we devised as a work of Myung-Gil Kim. And the idea is called combustion processing. And what you do is, rather than trying to overcome this energetic barrier as you do in a conventional sol gel, you build energetic constituents, if you like, fuels, inside the solution we're going to inkjet print or spin coat. So you generate atomically local heat. And so, at a small input in temperature. So this is, say, thermal data. This is the combustion synthesis. This is conventional. And you can see how clean at low temperature the combustion synthesis mass loss drops down compared to the sol gel. This is DTA. And again, you can see the combustion material lights off. And these are some transistors then. And this is the mobility you can get at 200, 250, 300 degrees from indium oxide. So you can get quite respectable mobilities at very low temperature processing. You can also do this with ITO. Now I hope this works. I don't get into trouble. In a minute, I'll show you a video. So this is a printed indium oxide transistor on aerolite plastic done by combustion processing. Mobility of now we're up to about 10 or 15. With sand, I'll show you it gets a lot higher. Very nice transfer plot. This is the leakage through the gate, very low. And it's on plastic, and he used, I believe that's silver source and drain. So this may be a disaster, but let me see if I can get out of this. And I want to show you a video of the combustion process. And the reason I want to show you is because it's so simple. Okay, here we go. So what I'm showing you is just a hot plate at 200 degrees centigrade. Clean laboratory. We cleaned it up. This vial is the combustion precursor solution. There it is spin coated on a silicon wafer. And that's it. You have a very good, smooth, you'll see when he moves the film, a very nice semiconducting indium oxide layer. Very, very smooth, no grain boundaries, works really well. So what can you do with this? I just want to, I don't get into trouble here. So as I mentioned, indium gallium zinc oxide, IGZO. You can go on the web and eBay and you can get an IGZO telephone made by NTT in Japan. I'm told that Samsung has ordered 20 million IGZO displays from Sharp, and that both Samsung and Apple have bought a chunk of Sharp. So these are looking at the IXZO series of compounds. It's a long paper in JCS, but just to show you, we're varying X from scandium, yttrium, lanthanum, and gallium. And these are bias stress tests of the transistor. This is gallium, IGZO, scandium, yttrium, lanthanum. It had only been observed empirically before that gallium was better. Why is that? And it turns out why it is the properties of gallium. It's a getter. It holds on to oxygen. When you lose oxygen in these transistors, when chemistry starts to happen, the threshold voltage drifts because you've changed the vacancies. And so it's a combination of the heat the enthalpy of formation of gallium oxide and the ionic radius. This suggests to you even better materials. We're working on that. Let's do some printing now. I'm going to show you a couple printing, but this is spin coating IGZO, and this is printed using our little Dymatics. We've now bought one of these Ceradrop high-resolution printers, but you can see very little difference in the properties on silicon dioxide gate dielectric of IGZO printed versus spin coated. But now let's go to that hafnium sand dielectric. There's a lot of stuff on this slide, but this is the IGZO, inkjet printed IGZO on silicon dioxide. Yeah, it's an okay mobility. This is on sand, the hafnium sand, so all solution processed, very low operating voltage, really nice transistors. If you go on the web, Sharp is now marketing an Aquos, which is their brand name, IGZO display. I'm pretty sure it's inkjet. I don't think it's OLED yet. But IGZO will deliver the current to light up an OLED display. So this just shows you some of the things that you can do and how these gate dielectrics we've developed enhance the properties. One last slide. So if you really can make amorphous oxides and tune their properties, and they don't have grain boundaries, they're flexible, you can also make a photovoltaic. So this is an inverted geometry photovoltaic cell, and we're using the PTB7, and just to show you the transparency, and it's on aerolite, which is an aryl polyester, and so it's completely amorphous, and we've doped it so it has good conductivity. And this is just showing you 3 cells, standard ITO on glass, amorphous ZIDO, zinc indium tin oxide on glass, and on aerolite, and you can see, in fact, the power conversion efficiencies look quite good. And it's stable up to 200 degrees C, where the ZIDO begins to crystallize. And the student built a little machine, and he bent it back and forth. I think this is about to go online in applied materials, hundreds of times, no decrease in efficiency. Okay, some conclusions. Our goal when we set out on this project about 5 years ago is room temperature fabrication of printed, flexible, unconventional electronic circuitry. What do I mean by unconventional? Not silicon. We're not going to compete with Intel or TI or whatever, but to do things that they can't do and which have unusual form factors, optical properties, mechanical properties. So we developed air-stable organic materials for CMOS, organic CMOS, high-performance gate dielectrics, hybrid organic inorganic circuitry. So I showed you inorganic semiconductors and an organic gate dielectric. That might be heresy, right? But no, our body is also a hybrid of inorganic and organic substances. And if each one contributes something uniquely, that we think that's very important. And the other thing to point out, and maybe subliminally, but theory and modeling increasingly are going to be essential as we design new kinds of materials. If we want to tune the HOMO, if we want to understand how we want the molecules to overlap, if we want to tune the LUMO, whatever, I think that's going to be essential for the next generation of materials. And not only applicable to organic transistors or unconventional transistors, but photovoltaics as well. And finally, I don't want you to think I did this all myself. It was due 5 groups at Northwestern spanning physics, chemistry, material science, really super group of graduate students, postdocs, undergraduates, and then a number of collaborators in the US and in Europe and Asia. And I think as Zaki has said at the very beginning, this has got to be an international collaboration. If you want to attack big problems, it has to be international and it has to be multidisciplinary. And so we saw a picture of Dresden. I visited Dresden. I was there during the jazz festival, which seemed really weird. You know, you walk into the airport and there are these New Orleans jazz bands playing. But it was a lot of fun. We also have jazz in Chicago. And so Northwestern is on Lake Michigan, just north of, we're the first suburb north of the city of Chicago. And finally, there's one other acknowledgement that to me is perhaps the most important at all, besides these agencies, and also Polyera, the spinoff. We now have 60 people, including 15 at a Taiwan applications lab. So we're making a lot of material and customizing it for customers. And finally, that of all my acknowledgments, to me, is the most important. So with that, I want to thank the organizers for inviting me, and thank you for your attention.